Hey, hello everyone. This is the movie clip number 3 in week number 2. Uh, Today, we're gonna learn some details of what the doping is. Okay? So doping, or the basic process of doping, is as follows: by placing or replacing, uh, just simply speaking, by replacing the silicon atom in crystalline silicon material with a non-silicon atom. Then we have done to dope the pure or intrinsic silicon crystalline material. So, for example, if you select a single atom from column 3 in periodic table, then some magic will be happened. In other words, the total number of holes, positively charged particle in silicon crystalline material will be modified. And what if we choose the atoms from column 5 in periodic table? Then the total number of electrons in crystalline silicon material will be modified. Definitely, in case of using substituting silicon atom with a impurity atom coming from column 5 or column 3, in either case, the total number of electrons as well as the number of holes would be modified together. So that total number of electrons and holes will be governed by the mass action law. So we're gonna learn that later. So here, as described here, by substituting or by replacing a silicon atom of silicon crystalline material with a special impurity atom coming from column 5 or column 3 element, then a conduction electron or free electrons or holes will be created. Okay, so let's see the detailed process. How come the conduction electron or holes are created by substituting silicon atom with a purity atom? On the left hand side, you can see a few examples of donors. So here, phosphorus arsenide. Uh, I have captured and took a part of the image of the unit cell that we have learned when we talk about the diamond structure stuff, right? So basically, originally it was a silicon atom, and on top of it there is another silicon atom bonded by covalent bonding, and on the bottom side in a triangular shape, at each corner of triangular, you can find out another three silicon atoms. This is a basic, structure, how the silicon atoms are combined and bonded with the neighboring silicon atoms, four neighboring silicon atoms. What if instead of this silicon, let's use arsenide or phosphorus? What would be happened? As I told you, phosphorus comes from the column 5 in periodic table, so that the total number of outermost electrons is 5 instead of 4 in case of silicon. So we're going to have an extra unbound electron, right? So this extra electron doesn't have any partner or partner to complete the covalent bond. So this bonding energy is, weaker than the bonding energy of this covalent bond. Okay? So at room temperature, at 300 Kelvin, this bonding can become loose, and this electron will become free electron or conduction electron. So equivalent word of conduction electron is free electrons, or simply electron. So here we can do this type of math. N sub d, the number of donor, is supposed to 10 to the 16 per unit volume. Can you guess how many electrons that we can have once all the donors will generate will, uh, donate, or all the donors will give the fifth outermost electron to the, single crystalline material. Can you guess how many free electrons that we can have? It's very easy. We have a total number of donors is 10 to the 16, and each of it can give or can donate a single free electron. So the total number of free electrons in silicon crystalline material is identical to the number of donors. Well, assuming that all the donors can donate its fifth electrons. In other words, once phosphorus can donate these free electrons, what would be happening in phosphorus atom? It is ionized, right? Positively or negatively. The atom of phosphorus has lost its one electron, so it's going to be positively ionized. So all the donors are fully ionized like that. If the total number of donors is equivalent to the total number of ionized donor atom, then we can simply say that, well, all the donors are ionized, or all donors are fully ionized. So that the ionized donors will determine the total number of free electrons or conduction electrons, or okay. So without any, some special comment or some very uh, specific, assumption to be used, you should always assume that all the donor atoms are going to be fully ionized. Okay, so total number of free electron is identical to the number of dopant atoms. Okay, then why this is so significant in modifying the conductance and resistance of pure silicon material? Previously, I mentioned that the free electron is created with the holes in pairs, shortly speaking, EHP. And what was the number of the free electrons in intrinsic silicon material? That was denoted as n sub I, and the value of it was 10 to the 10 per cubic centimeter. Take a look at the doping concentration, how high, how dense the donors are within a unit volume. That was 10 to the 16, which is way higher than the intrinsic uh, electron concentration. So the total number of electron is governed by donor's concentration, which is much higher than the intrinsic electron concentration. So intrinsically, uh, the pure silicon material can have its own free electrons and holes. However, the total number of intrinsic carrier concentration is simply 10 to the 10 per cubic centimeter. But now we injected 10 to the 16 donors atoms into the silicon atom, into the silicon crystalline material, so that this number can become negligible. Okay, so total number of free electron is only governed by donor concentration. Okay, let's erase them and let's move on to the next one. Acceptor. So here, originally, silicon atom was there. However, if we replace this silicon atom with a boron coming from column 3 in periodic table, then what would be happening in this unit cell? Because the boron comes from the column 3 in periodic table, how many free electrons no, 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 no. How many outermost electrons available in case of boron? Is column 3, right? So that the total number of outermost free electrons of boron is simply 3. But it requires to make a bond with 4 neighboring silicon atoms. So single electron is lacking. In other words, some other free electrons, maybe this is, uh, at room temperature, free electrons are always available. Think about this value, 10 to the 10 per cubic centimeter, right? At room temperature, without any dopant atoms, the crystalline silicon material has already 10 to the 10 free electrons available. Definitely, as well as free holes as well. These free electrons would like to have us have fill out this empty space. Then this empty space will come out, and this empty state is denoted as H plus and named as hole. Okay. Previously, I mentioned the hole is a kind of the other type of carrier in silicon material, but its direction of movement of electron is quite opposite to the direction of free electrons. So that people are using the positively charged particle or a carrier. Okay. All right. So boron can create a single hole. So we can do this simple math again. The total number of acceptor, denoted as n sub A, is supposed to 10 to the 17 per cubic centimeter. Then how many holes can be created in this case? In this specific silicon sample, topped with an acceptor of 10 to the 17 per cubic centimeter. Well, as long as all the acceptors, I mean the all the boron atoms are ionized, in other words, all the boron atoms are accepting all the free electrons to complete this covalent bond, then it's going to be ionized. Because it is accepting electron, it's going to be negatively ionized. So Na minus is equal to Na, assuming that all the acceptors are fully ionized. All the acceptors are fully ionized. Okay, so uh, when it comes to the uh, acceptors, the role of acceptors is as follows. The total number of free holes, or simply hole, positively charged carriers in silicon material can be modified by the acceptor concentration. Okay, all right. So let me draw the bonding model herein. Here is a silicon atom, but this silicon atom is now doped and replaced with donors. So suppose that that is arsenide. Okay, in two-dimensional bonding model, it's going to be like that if I draw the two-dimensional bonding model. And electron, fifth electron is relatively loosely bonded with the arsenide atom. However, at room temperature, because of the externally applied thermal energy coming to this arsenide atom, this bonding energy should be much, much weaker than the bonding energy of these covalent bonds, so that it is more likely for this fifth electron to break and it will become the free electron. Okay? Then this arsenide will become possibly ionized. Okay, here one more note is possibly ionized arsenide. That is immobile carrier. So because it is not mobile, we cannot say it is carrier. Okay? I would say possibly charged arsenide is immobile. So loosely bound fifth valence electron of arsenide atom breaks free. I'm talking about this physical event and becomes a mobile electron for current conduction. So in pure silicon crystalline material, uh, how many dopant atoms, how many donors are doped into the silicon crystalline material, the total number of free electrons for current conduction can be determined. Okay, so remember this equation. And let's move on to the next case. Example, add boron atom to the silicon crystal, then what would be happen? So let's draw the two-dimensional representation how the boron atoms are bonded with the four neighboring silicon atoms. Okay, then as I told you, the boron comes from the column 3 in periodic table, so it is like the total number of outermost electron is total 3. 1, 2, 3. Then here, this electron comes from silicon, but boron don't have any more outermost electron. So this state is empty, vacant. So the other free electrons would like to uh, have itself more stabilized. In other words, in terms of total energy that this free electron has, it is more likely to lose its high energy to become to stabilize itself electron. So it is more likely to fill in this empty state. Then this hole will move to the other site. So suppose that there is another silicon atom, silicon to silicon bond, and suppose that these free electrons would fill in this site and the hole is created and this uh, hole and I will say it is okay, there is another bonding here, bonds here. Okay. Then this free elect I say instead of free electrons to in order not to confuse you too much, suppose that this electron for some reason because of the externally applied thermal energy from room temperature, the electron is now filling out this empty state. Then this bond, this covalent bond is lacking a single electron. In other words, here is another empty state. And I would say this electron would like to fill in this empty state. Then this covalent bond is lacking a single electron. So here is a hole. So take a look at how the empty site is moving. So originally empty site was here and the second electron is was filled out, you know, was this empty state was filled out with a second electron coming from this covalent bond, and we can find out the hole can be found here. Originally here, the second site that this empty state can be found here, site number 2. And the last position that we find the hole is here, site number 3. So the hole is now moving in this direction. But take a look at how the electron has been moved. You know, electron is now coming to here and then move to here. So take a look at the direction, how the electron is moving and how the holes are moving. It's quite opposite, right? But we know that electron is negatively charged, so that we can simply make a conclusion that hole is positively charged carrier in silicon material. And how come the single hole has been created? Because of what? Because of the boron dropped into the silicon crystal. Okay, so uh, as described here, the boron atom can accept a single electron from a neighboring silicon atom, right? This electron was originally participated into completing the covalent bond and resulting in a missing bonding electron or hole. So the hole is free to roam around. It is move around the silicon, that is material, silicon crystalline material carrying current as a positive charge. That is, some illustration how the holes are created and how they are moving around and roam around the silicon crystalline material. So the silicon crystal material is kind of playground, and onto the playground, the holes are moving here and there, carrying current. Okay, so that's all for some detailed process how the donors and acceptors can create electrons and holes. And remember that the total number of free electron is totally governed by total number of donors, and the total number of holes is fully governed by the number of acceptors. Donor electron, acceptor hole. So these, partnership or combination, you should remember. Okay, so I guess let me stop here. And in the next movie clip, I'm going to explain uh, where the energy level is and where the acceptor's energy level is in the band diagram. Okay, in pure silicon material, the band diagram was very simply drawn. Two, solid line or parallel two lines. That's it. But shown in this slide, we need to understand the energy state for donors and acceptors. So we will do that in the next movie. So take a short break.